Find the volume of the solid that lies under the elliptic paraboloid, this, and above the region D bounded by these two curves. So we need to graph the region D. So x equals y, that's just identity line, y equals x, or x equals y, same thing. This is x equals y. Now x equals y square minus 2, how do you graph this? As you know, x equals y square, parabola but slanted like this. And x equals y square minus 2 means shift this down 2. So 1, negative 2 here. So the graph will be something similar to this. It does not have to be exact, and here is the case. This is the graph of x equals y square minus 2. So the region bounded by these two curves is this. Now we need to find the points of intersections, this point of intersection and this. If you graph using your calculator correctly like this, then this is 2 and this is negative 1. This is negative 1 and this is 2. Or algebraically we can set these curves together, because x equals y square minus 2. That means y square minus 2 equals y. Bring y to the left side, y square minus y minus 2 equals 0. Factor. Okay, from here you get y equals 2. From here y equals negative 1. So 2 obviously here and negative 1. Okay, now we would like to identify whether this region is type 1 or type 2. If we draw vertical lines here, then we can be from same curve. I mean, if we draw like this curve to the same curve, so it can be type 1. Okay, let's try type 2. So we can draw this line, arrow, then we get first curve here, left curve, this is x equals y square minus 2, and right curve x equals y. In fact, this is already given in terms of x equals a function of y, so that's type 2. So we can say this is type 2. Then we don't have to write this, but we can always write this region D. D is all x, y such that x has bounds. Look at here, x left curve is this. Left curve is y square minus 2. Y square minus 2. And right bound, right curve is x equals y. And y has bounds, look at here, negative 1 to 2. So negative 1, 2. Okay. Then the volume of the solid that lies under the elliptic paraboloid is given by just the double integral on this region for this function 3x squared plus y squared dA, which is, now we are saying type 2. Type 2 means y outside, y equals something, so dy. Now y has number bounds, negative 1 to 2, look at here, negative 1 to 2, and x are given as a function of y. X has bounds, lower bound y square minus 2, upper bound y, and we got the same function 3x squared plus y squared, dy outside, inside is dx. Now we just evaluate this iterated integral. We can just do this first, then go outside. Okay, so inside is now, this is y equals negative 1 to 2. Let's integrate this function with respect to x. So 3x squared, that's 3 times x3 over 3. So just x cubed plus y squared, bf's like a constant with respect to x. So this is y squared x. Okay, and that derivative of y squared is a constant, y squared x. And we want to go from here to here. So x equals y squared minus 2 to y, and we have dy. Let's evaluate this. This is y from negative 1 to 2. Replace x by y. So this is y cubed plus x equals, okay, y squared times y, so y cube, that's 2y cube upper limit minus lower limit, so x cube means y square minus 2 cubed, y square minus 2 cubed, okay, is a negative sign, so we need to put bracket because negative gonna change sign later, plus y square times x is y square minus 2, so this is y square times x is y square minus 2, and we have dx. So let me simplify this. So this is, now we have only y, so we don't have to write this anymore. Negative 1 to 2, once we multiply 3 times we get this, plus distribute y squared we get this, and negative 1, there is nothing, means negative 1 here, distribute negative 1, so we get this. Now we can integrate each term. In fact, if you like, you can combine 2y cube minus 12y cube, that gives negative 10y cube. When you integrate every single term, then you evaluate at upper limit 2 and evaluate at lower limit negative 1, calculus 1, you get 225 over 14, which is 16.07. Okay, these are dy. Final